Okay, seems like there's no other people, but I think we can start first because it's being recorded. Okay, so uh, hi, I'm back and I'll be covering dynamics today. So this is quite a long chapter, so uh, most of the lesson will be going through content now. I think I'll have around 15 minutes to like answer any questions or like go through any questions in the problem set. So uh, yeah, if you guys have any requests, you can just say them along the way. So last lesson we did kinematics, and in kinematics we basically just discussed everything about motion, like velocity, acceleration, and everything, but we didn't care where the motion came from. So now in dynamics, our goal is to understand where this motion comes from, and it is through forces, and through that you also have concepts such as momentum and energy and power, which we'll look at in this chapter as well. So the first section is on Newton's laws, and this should be trivial to you guys by now, like basically the three laws and like how to apply them. So uh you can just like briefly read through this on your own as a recap, but it should be quite trivial lah. So this first example here basically is a normal application of Newton's laws along different axes. So here it is most convenient that we chose axes that are parallel and perpendicular to the plane, to the incline. And by doing that, it's more convenient because our normal forces and our friction force is perpendicular and parallel to the incline respectively, and we want to find them. So it's more convenient to resolve our forces like that. So yeah, this is detail. So yeah, just by simply applying Newton's second law and balancing forces, you can just get these stuff. So nothing too fancy. I think this is covered in like normal school physics. So yeah, should be all right for you guys, I hope. Okay, so the second part is a bit more interesting because it is quite a common mistake for most people to leave out one of the two cases that you have to consider. So I think most people would consider the case of the applied force being too small. So if we go to the diagram here, if the force of mg that's applied to the block is too small, then of course the block will slip, and it will slip downwards because you're not applying enough force to keep it from slipping downwards. So I think this is the intuitive one. But there's one case that might be less obvious or like more easily messed up on, which is if your force applied is too large. And if it's too large, your block will start slipping upwards. And that's also not what you want. So it's quite important that you don't miss out cases like that because because such tricky cases do appear sometimes, uh, even in SPhO. And yeah, you just don't want to throw away marks lah for not remembering cases. So here I've done the analysis for both case one and case two. Uh, so you can see that the analysis is also quite simple. It's just applying Newton's laws and what you have already learned. Uh, yeah, and then you get two extreme values of theta here. So your range of theta is bounded by these two extreme cases as given like that. So you realize that if you forgot one case, uh let's say you forgot case two, you forgot that the applied force can be too large, then you won't have you won't have this. Then you won't get this bound for theta. And this means that your theta is unbounded in one direction, which doesn't make sense because how can your data get as small as you want and still have that plot and uh still have it not slip. So it's quite important that you can think about this physically so that you avoid uh missing out cases as well. So yeah, the main point is data cannot be unbounded in any direction, positive or negative. Yeah. So uh so the main point of this question is don't miss out cases in dynamics, especially statics problems like that. Yeah. Okay. So I hope that was fine. With that, we'll move on to more concepts because just using Newton's second law like that is not enough to solve most Olympiad questions on mechanics. So before we move on to the other stuff, I'd just like to discuss one problem here on how we choose systems for analyzing forces. So what does a system mean? So you're free to choose any objects that define your system. So in this case, in example 1.2, you have a lot of blocks. You have n identical blocks. Each of them have mass m. Each of them, and between every adjacent block, they are connected by strings, and there's friction with the ground. So your goal is to find the ith tension in the string between the ith and the ith plus one block. So you have a lot of objects here, and clearly you're free to choose whatever you want as your system. So what you can do is, uh, oops, okay. So there are a few systems you can go with. For example, you can say, oh, I want to choose all the blocks and strings, basically everything as my system. But another person can also say, I want to choose one particular block. Let's say, the ith block. That's my system. Another person could also say, I want to choose, for example, a few blocks. Uh, let's say this person chooses the first block to ith block as the system. So you can see here that there's many choices of systems that you can use. And the thing is, none of them are wrong. So all of them can be useful, except some are more useful than others. Yeah. Okay. So why do we choose different systems? Because when you choose a different system, your internal forces within the system are different. So this means that when you analyze the whole system, you are free to just disregard the internal forces within the system of choice. So what I mean by that is, for example, if you chose your system as all the blocks, so the first choice there, so if you did this, then you can imagine drawing like a uh draw like a rectangle around this that encapsulates everything. So that's your system. So if you do so, you can see that this force F here effectively acts on this whole rectangle that I've just drawn. And when you do so, all the tensions the within the system, all of these are internal forces. So all the tensions are ignored. And that's very good because you don't have to deal with all the nasty tensions anymore. So by doing this, you can write your Newton's second law as this. So basically it looks like this. Yeah. Where your Yeah, and your friction is kinetic friction, so it's the same for each block. So you have one equation like that. So another person says, "Oh, I want to look at the first to ith block as my system." Okay, that's also perfectly valid. So now instead of drawing the rectangle like that, we draw the rectangle like that. Okay, and that is our system now. So as you can see, this rectangle still has the force F here. There's also a tension Ti here, and then there's uh the net friction force here. Uh, the If. So you can see here that you get another equation by considering another different system and the forces that act on the different system. And you can see again that all the tensions are ignored because they are all internal forces within this system of choice. So by doing this, you have your forces F, Ti, and If. You get another equation using Newton's second law. So that's nice. Now the third person says, let's look at the ith block to the nth block as our system. So what the third person means is we do this. We draw the rectangle here. So now with that, we can see that if you do out your forces again, uh, you will get this as Newton's second law by considering the forces that are acting on this system. Wait, sorry. Oh wait, no, wait, sorry. I think that's a typo here. This should be okay. I plus one to nth block. So yeah, small mistake here. So this is our rectangle. Then you have a tension Ti here. Then uh you have your friction where your friction acts on n minus I blocks. Yeah, and then you get that. So you can see that just by choosing different systems within the same setup, you get different equations, which allow you to solve for what you want. So here we have three simultaneous equations in the variables of in the desired variables. So you can just solve it for Ti. And yeah, so that's nice. So the point of this question is to get you to realize that you are free to choose your system however you want. So there's technically no wrong system, but it's just that if you choose a system that is not intended, you will not get useful results. So for example, uh if I went to do system two here, if I choose this, then I will not get any useful result because all I'll get is an equation involving two adjacent tensions and one friction, which is not exactly what I want. So I would say that this is a bit more useless. Yeah. So unfortunately, there's no like hard and fast rule on how to choose your system properly or correctly to make it useful. I think it kind of comes with experience. So just try as many like different systems as you can think of, and see which ones give you useful information. Yep. In general. All right. So that's on choosing your system. Okay. Of course, we also have Newton's third law, which should be uh trivial by now. Yeah. Okay, so we'll move on to our first possibly non-trivial concept on systems of masses. So when you have a lot of masses, let's say you have a coordinate system, then you have your x and y axes. Say you have random masses everywhere, and we also draw the position vectors of these masses. Yeah. Okay, so let's say you have three masses here. Now, suppose that these masses are undergoing some. Okay, suppose that there's some force that's going on within the masses, or like some force that's pushing all the masses along. Now, it's going to be quite complicated to analyze F equals ma on every single particle. So here I've only drawn three particles, but what if we had 3,000 particles? Like, I don't think anyone would want to write 3,000 F equals to ma equations for each of the particles. That's why we developed simpler methods, such as considering the center of mass. So, what is the center of mass? So let's say that you have n discrete point masses. So this is important. Discrete point masses means that you have n masses that are treated as negligibly small and are treated as basically different masses that are apart from each other. So in this case, what I've drawn here corresponds to three discrete point masses. So you can see that they have masses m1, m2, m3 with position vectors r1, r2, and r3 here. So the definition of the center of mass, or I'll just call it the CM for short from now on, this is located at this point, given by a summation. So an easy way to think about why this formula is true, is to just think of it as a weighted sum of masses. In this case, the weights here are the positions of the masses. So yeah, for those of you who know what a weighted sum is, I think this is an easier way to think about it. So that is for discrete point masses. But there's a clear problem to this because most objects in real life, they're not well modeled by point masses. For example, your computer in front of you is not it's a continuous mass distribution, and it's not just a point mass because it has size to it. So instead, if we have a continuous mass distribution, then we have to use integration. So the CM for this case is just given by this integral. Or if you want in Cartesian coordinates, you can find the x, y, and z positions of the CM given by these three results here. Again, this is also saying like this is also saying that it is a weighted sum of masses. Except now because it's continuous, we replace the sigma with an integral. So yeah, these two are actually equivalent in a sense. Except for except this one is kind of taking n to infinity. You can think about it this way. Yeah. So in the context of SPhO, you likely only be applying this to find the CM for situations where you have symmetry along one or two axes. So you will see an example here in example 1.3 on what it means by symmetry. And if you have symmetry, you can very quickly deduce the position of the CM along these axes. So here in this example, we have a non-uniform cone of a base radius of r and a height of h. So I'll just draw it out again. So the tip of the cone is at the origin here. Uh, yeah, here. So you're given that density varies along the z-axis. So density is non-uniform. And we have that rho z is kz cubed for some constant k. We want to find the position of the CM. So what does symmetry mean here? So symmetry just means that uh, because your cone is the central axis of the cone coincides with the z-axis. This means that there is no reason for your CM to not be at x equals to 0 and y equals to 0 because your density is not varying uh, along these axes. Your density only varies along the z-axis. So you can see here that rho varies only along z, and cone's central axis is the z-axis. This means that xcm and ycm have no reason to not be at 0. And that's just what symmetry means. So you can see here that because the non-uniformity only occurs along the z-axis and there's symmetry of the cone through the z-axis, you can instantly conclude this. And this should be something that you should see instantly when you do when you find the CM of stuff. Okay, so now great, we have the coordinates of the xCM and yCM. So we are left with the zCM. This is the part where we just apply equation 3 here. So for the zCM, the easiest way to do this is to consider infinitesimal masses. So remember our cone here. So let's say I consider some arbitrary height at z. Okay, delete this. Okay, so let's say I consider some arbitrary height at z. And let's say I call this smaller radius r. So we can just redraw two triangles as such. And both of these are right triangles. And clearly the angle here, this angle, is the same for both triangles. So this means that these two triangles are similar. And thus the ratio of lengths will follow this, which means that r equals to dr over h. Yeah. So that's what we did here. Now for that we just have to substitute in our formula. So when we do this, when we move along the z-axis, we are essentially considering how infinitesimal disks work. So how the disk looks like is like that. So you're considering slices like that. Oh, I have to stop deleting this. Okay. Okay, so slices like that. And these form your masses. So your dm is an infinitesimal mass here. It's just equals to rho dv because that's how mass density and volume are related. Now, what is your dv? You have a slice of a disk here. So your dv is just going to be this, where this is like your circle area, and this is like your height of the of this. So your dz is just here. Okay, so your dv is that. So plugging this in, dm equals to rho pi r squared dz we know that R is this, so let's return it back here. And we also know that rho is kz cubed, so let's return it there as well. And we have this. Then by definition, you can just plug in this, and that should give you uh 6. And we integrate from 0 to h, and just grind through all the math, you should get 6/7h. Yeah, 6/7h. So this is how you find the CM of a continuous mass distribution. So why is finding the CM important for this case? Because the position of the CM is the point where the total gravitational force effectively acts. So this is important because we are looking at the total gravitational force. So for the cone here, if we have this, then uh, if we know the total mass of the cone, which you can find as well, you can show that for analyzing forces, total the total gravitational force effectively acts at this position of the CM, which is useful when you're doing stuff like uh when you're doing stuff in future chapters in rotation. This would be useful when you want to know where the force acts. Yeah. So in general, these kind of problems are more math related because it's just about how you set up the integral for equation 3. So just have to practice a bit for this, and you should be able to do these kind of problems easily. So something that is perhaps more interesting about the CM is when we look at the CM of an isolated system. So isolated system just means F equals to 0. So of course you have Newton's second law here. And when F equals to 0, this means that A equals to 0, which means that it does not accelerate. The CM does not accelerate. And the CM does not, and A equals to 0, this implies that dv dt equals to 0, which implies that V is constant with time. So if V is constant with time, if your CM was initially at rest, if V is initially 0, then the CM will always have V equals to 0, regardless of what the time is. So we call this the conservation of CM, which is also referred to as the non-movement of the CM, which means the CM doesn't move. So why is this important? So this example will show you how you can use this quite elegantly. So here we have a boat of length L, ms, m. So I will draw the setup out. And we have a dock of mass small m, the left end of the boat. So this is floating freely in water. What this means is that there are no other forces that interrupt the boat's motion or damp the boat's motion. So now what happens is that this small m here goes to the right end of the boat and then stops. We want to find how much the boat has moved from its initial position here. So the way to do this, as you expect, is using the conservation of CM. And why this works is because if we consider this as our system, uh, well, F equals to 0 on this system. F external equals to 0 on this system, which means that conservation of CM can be applied. Okay, so now that we established that it can be applied, let's see how we can apply this. So I would first define a coordinate system here where I let my initial left end of the boat be x equals to 0, which means that my initial right end of the boat is at x equals to L. So this is the initial setup. Now, my final setup will look like that. So I will extend this here. So you can see that because the small m moves to the right, but the cm position has to be the same. This intuitively means that the big M must move to the left. So we can expect the boat to end up somewhere around here. Somewhere around here, yeah. And this is final. So now your small m is at the right, and your big M is somewhere here. Let's call this distance x. So initially, your cm here, the location of the cm using this coordinate system is simply given by this, which is equal to this. Now this L over 2 here comes from the fact that the comes from taking the center of the boat. So we are taking this point here. So yes, of course, we are assuming that the boat is uniform. So see that we can see that the cm is somewhere around here. Now, by conservation of cm, the final cm is equal to the initial cm. So now, how do we express the final cm in terms of x? So we see here that if the boat has moved by x, then the center of the boat now oh yeah, also we'll define this x to be less than 0 because it moved to the left, consistent with how our signs are defined in our coordinate system. Okay, so the center of the boat is now at uh, x plus L over 2. Dot is at x plus L. So with that, our final CM will just be m x plus L over 2 plus m x plus L over m plus m, as you can see here. And this, after some algebra, will simplify to x plus m plus ml over 2 plus ml over m plus m. Yeah, after some algebra. Now what's left to do is, using this, we can say that this is true. And with that, with more algebra, we can eventually find x. And your x here is, yeah, your x here is this. A lot of algebra. Okay, so let's take a moment to make sense of this result. So the first thing is x is less than 0. Okay, that's what we expect, which means that the boat indeed moved to the left. Expected. So that's good. Second thing, this result for x, it only depends on m, small m, big M, and L, which means that it doesn't depend on For example, the v dot, the speed of the dot doesn't depend on uh it doesn't depend on how the dog moves at all. So whether the motion of the dog is uniform, non-uniform, whether he moves anyhow, we don't know. And in fact, we don't care because that is the beauty of conserving the CM. So in general, if you have a complex motion that's between two well-defined states, this idea can be used. So what so let's break down what this means. In this example, the complex motion is just the dog's run because we don't know how the dog ran. It could have ran anyhow and we don't care about it. And our two well-defined states are the start and the end of the motion, which is before the dog started running and after the dog stopped running. So because these criteria are met and your system is isolated, conservation of CM applies and you can simply do that. So yeah, interestingly, it doesn't depend on the dog's velocity or how it runs at all. So that's quite nice. Yeah. Okay. So that's about conservation of CM. This idea tends to pop up quite a lot, especially when you have especially when things might not be so obvious at first glance. So sometimes it might be hard to form an equation using what you have because, for example, they don't give you what happens in the complex motion. So there might be some super complex motion going on and you don't know what's happening there. But don't worry about it because sometimes it just boils down to using conservation of CM and you realize that it will all work out. Yeah. Okay. So we'll move. Okay, I will give you guys a short break actually for this lesson. I'll give you guys a break after we finish everything up to the ideas. So yeah, let's just push on for a bit more. Okay, so next concept is momentum and impulse. I think you guys should have seen this before. Uh, maybe not five, but it's just saying that. Uh, oops. Yeah, it's just saying that if you have any random function, you plot force against time, the area under that is your impulse. Yeah, so nothing too fancy about that. So impulse momentum theorem will relate your impulse to your change in momentum. Okay, so the first concept is the conservation of momentum. When there's no external force, your total momentum is conserved. And this we usually just call it the COM. So when we deal with equations, you might see me just say COM and stuff like that. So I'm referring to the conservation of momentum. So what this means is that if F equals to 0, P equals to constant. Yeah. Or if you have a net external force, if your F is non-zero, then we relate these two using this. F, F equal to dp dt. But you also saw just now that from Newton's second law, you can easily see that this should be F equals to ma instead. So why are there two different definitions of F? Well, very technically, the correct one is this one. Reason being this one assumes a constant mass, which might not be true, and so it's not correct. Not exactly correct. So yeah, in reality, the equation A is more correct. So you see how to apply this to changing mass systems because it's essential that you use the correct form of Newton's second law when your mass is changing. And you see this later on in the ideas section. So let's move on to something uh that's perhaps closer to you guys first. So it's on collisions. So for collisions, in all collisions, your total momentum is conserved. I think most of you should already know this. But we have different types of collisions as well. We have perfectly elastic collisions. We have perfectly inelastic collisions. And by the you can probably tell by the name that perfectly elastic means that your objects collide in a way such that the total kinetic energy is conserved. But for perfectly inelastic, the objects simply just stick together and they have zero relative velocity after collision. So I can just draw a few diagrams here. So perfectly elastic, you have such a case like that. And here we can, here what is conserved, momentum and kinetic energy. Perfectly inelastic, it will instead move like this. So it just moves together as one. And they move with the same speed. Okay, in this case, what is conserved? Only momentum. Clearly, some energy has been lost because you know from daily life that when two things collide and stick together, they produce sound, there's heat, etc. So energy goes somewhere. So yeah, kinetic energy is not conserved for an inelastic collision. Okay, so we also tend to define this thing called the coefficient of restitution, or we just call it the COR, or we just call it epsilon. This is a ratio that relates the relative speed of separation and the relative speed of approach. So in this case, I can use the perfectly elastic one as an example. The COR, epsilon, would just be given by relative speed of separation, which is this, over relative speed of approach, which is this. So so this is how the quantity is defined. So one quite subtle thing here is the signs. So you can see that the signs in this equation are written in this way, which might not be very intuitive at first glance, but it might be perhaps more intuitive to just remember it in terms of relative speeds. I think it's clearer to see how the signs work if you think of relative speeds, whether they are in the same direction or the opposite direction. So yeah, if they are going opposite directions, it's a plus. If it's the same direction, it's a minus. So yeah, so you have this. So this is perhaps more intuitive. So what are some properties of the COR? Well, it's a ratio and it will satisfy this. It will always be between 0 and 1, both inclusive. And you can see that for a perfectly inelastic collision, epsilon equals to 0 because 0 relative speed of separation, because they move at the same speed away. And perfectly elastic collision will satisfy epsilon equals to 1. Then another property is that this COR can only be applied along the line of impact. So what is a line of impact? This might be a bit subtle. So we'll go into that in example 1.5. Now, so just a short interlude before we go into that, to see how the COR comes about is essentially, so let's say we take the case of a perfectly elastic collision. We can write COM and COE, which is conservation of kinetic energy. So we can write two equations as such. So you can always write equations like that. So actually you can simply get the fact that from these two equations, simplify. So after some massive amount of simplification, you should be able to get that epsilon equals to 1 for elastic. So you can just try this out yourself as an exercise later on. I won't go through this in the interest of time. Yeah. Okay, so now let's look at what the line of impact is. So let's consider this example. We have two parts here. They are on a frictionless table, and the collision is not exactly head on. You can see here that A is colliding with B, and the centers are not exactly aligned. So what happens because the centers are not exactly aligned is that you have a sort of what we call an oblique collision, and they move off in different directions here. So we want to find the final speed of part B and the unknown angles alpha and beta. So of course this looks like a standard question, right? Like you can solve it in a standard manner. Just write. So what you can do is you write COM along the x-axis, COM along the y-axis, and then COE for your kinetic energy. And we can do so simply by just saying you can just do this. For this it would be uh and for this it will just be this. So we have three equations here from writing two COM equations and one COE equation. And theoretically you can solve this instantly because well you have three unknowns and you have three equations. So you can solve it. So you might ask, okay, so it looks like a standard question, right? So why are we going through this? Because there's a more elegant way of doing this using the line of impact. So you can see here that there's this red line here, red dollar line here that's being drawn here. So this is what we call the line of impact. The line where the, the line where like the two parts sort of impact each other. So we can simply apply the coefficient of restitution along this line of impact. So what we can do here is, firstly, we can, as per normal, conserve momentum. And in this case, I choose a direction that's perpendicular to the line of impact. So I choose this direction to conserve momentum. And I can write this here because it's quite simple. The equation is simple because B never has momentum along this axis. Now, I will now use epsilon equals to 1 parallel to this line of impact because here I said that COR can only be applied along the line of impact. So I'll use it. And by using it, I will get this by just considering the relative speeds. So how you see this is uh, so you can just draw this VA1 here initially. So how you see this is initially this is the relative speed because B is stationary. then this is the final relative speed. Because uh because B because B is moving in this is VB2, then you have VA2 here, and you have alpha plus beta. Yeah. So we can just write this as our epsilon equals to 1 equation. And of course, not forgetting you can conserve kinetic energy, so you have this equation as well. So now let's look at this, what we did here versus what we did up there. So let's compare these three equations to these three equations. You can see here that there's quite a drastic difference in a way that the three equations on top, they are much more, okay, maybe not much more, but they are more complex because they involve MA, then there's MB, then there's a whole bunch of other stuff. But in our first two equations here, there's no MA and there's no MB. So it's quite elegant over conserving momentum in the X and Y axes. So yeah, I've written it out here as an exercise, but they contain MA and MB, so it's quite messy to deal with them. So it's easier to deal with doing this sometimes by using epsilon equals to 1 for perfectly elastic collisions. And I hope this example shows you why. Okay, so up to now, this should be hopefully quite familiar on collisions. Now, we'll go into something a little bit more unfamiliar about collisions, and this is what we call the CM frame. So I want you to recall from kinematics on what a frame is. When we want to go between two frames, let's say we have let's say we have V1 and V2. And let's say the frames move with relative velocity V. So let's say we have two frames, the S frame and the S prime frame. And the S frame sees V1 and the S prime frame sees V2. And S prime moves with velocity V with respect to S. So how do you relate these velocities? Well, the way to relate them is just this. So this is how you transform between frames. Now this is quite important because we are transforming between frames in this trick. So what are we doing in this trick? What we are doing is we are going to this thing called the CM frame. But first we have to define what the velocity of the CM is before we can even transform it. So this is what we define it to be. And this is nothing more equivalent to just this. So you can just see that by differentiating the position of the CM, you get the CM velocity. So this is what we define as the CM velocity for two masses M1 and M2. And an important property about this is that in the CM frame, the total momentum of the system is zero. So this is very important. And you can show it, you'll be showing this later. Okay, so from what I've shown here just now, this is how to transform between frames. So this is equivalent to that. And we'll see how to apply this. Okay, so uh, so yeah, okay. So let's say we have two masses here, M1 and M2, and they have lap frame velocities V1 and V2 respectively. Now we want to make them into the CM frame, right? So we can simply use equation 11 here and plug it in for V1 and V2. then we can find V1 cm and V2 cm. So there's nothing fancy here other than just using this and using that. Now at this point, it is worth verifying that the total momentum is zero. So you can see here that uh, with these two, m1 v1 cm plus m2 v2 cm is actually equals to zero. So total momentum is indeed zero in this frame. So after you find this, uh, because momentum is conserved, right, and your initial momentum is zero in this frame, this means that your final momentum will also be zero. So this equation also holds. Here we'll be using prime quantities as after the collision. So this also holds. Now you rearrange this, you will get this. And the significance of this just says that V2 cm and V1 cm point in opposite directions because they are related by a scalar, negative m1 over m2. And m1 over m2 is positive. So this means that these two vectors have to point in opposite directions. So to see what is happening, you can refer to this diagram here. So let's say M1 and M2 have V1 and V2 respectively in the lab frame. We go into the CM frame, then they have the new speeds V1 CM and V2 CM, where the total momentum in this frame is zero. And after the collision, they will leave like that, opposite to each other in the CM frame. Now, so just a small remark here, if you use the CM frame, you have to be very careful. Always convert back to the lab frame after dealing with the CM frame. So for example, don't just end the question saying that, okay, the two masses will move opposite to each other in the CM frame. Because most of the time, what the problem wants is usually some lab frame quantity and not a CM frame quantity. The CM frame is just a convenient tool for you to analyze collisions. Okay, so this might be a bit abstract. So let's see this example and how we use it to solve collision problems with the CM frame. So here we have a mass M1 that's moving. Let's say we call this B1. And we have a mass M2 initially at rest. Okay, we want to find the maximum angle of deviation of M1. What this means is uh, you want to find what is the maximum theta here that can happen with this collision. Okay, so if you didn't know okay, this is also elastic. Okay, so if you didn't know what the CM frame is, the most naive way to do it would just be, okay, M1 V1, okay, COM X, COM Y, COE. This is a very naive way to do it. So we write M1 V1 equals to M1 V1 prime cosine theta plus M2 V2 prime cosine phi. Okay, blah blah blah. It's quite similar to the above example here, which I did. Uh, wait, yeah, this one. It's quite similar to this one. So you write something like that, and it's not wrong because once you do this, you can just eliminate variables, and then you can get around to a point where you can maximize theta. So it's not wrong, but why go through all this math if you know what the CM frame is? And so I'll show you the easy CM frame solution. So let's start by finding the CM velocity. In this case, because only M1 is moving, the CM velocity is simple and it's given by this. So yeah, so that's just the CM velocity. Nothing fancy so far. Okay, so now you have the CM velocity. Let's go into the CM frame. So if you move M1 into the CM frame, you have V1 uh V1 minus VCM, and you get this. and you have V2 minus VCM, and you get this. Okay, so nothing fancy also. It's just doing a whole bunch of manipulation. And yes, indeed, as a way to check, this is true, which means that up till now you are correct. So now is where it gets a bit subtle. So you see that after the collision, your v1 prime cm, your final velocity of v1 in the cm frame, it can go in any direction, but you don't know this direction yet. But regardless of whatever happens, in terms of vectors, this will always hold. v1 prime equals to vcm plus v1 prime cm, where v1 prime is the final velocity of v1 in the lap frame. And this is true by definition, because this is true by how you define going between frames. So this is always true by definition, no matter what the direction of v1 prime cm is. So we have this relation here. But the good news is, because the collision is elastic, energy is conserved, we can uh, we can write this in the cm frame. So this holds in the cm frame. And you also have this equation here, with equation 15. Yeah, equation 15. You have equation 15 here that relates v2 prime, v2 cm prime to v1 cm prime. So this is just equation 15. Then by taking the modulus of both sides, you will get this. And by substituting this into this, you can simplify a whole bunch, and you will actually eventually get that v1 v1 cm prime equals to v1 cm equals to m2 over m1 plus m2 v1 in terms of magnitude. So actually, the speed of m1 remains unchanged after an elastic collision in the cm frame, which is very good because now you know the magnitude of, so you know the magnitude of v1 prime cm. So you know this, which means that if you draw a vector diagram that shows this relationship, which we know is always true, right? So let's show this relationship with a vector diagram. So you can see here that these vectors add up like that. And here we draw a semicircle around the center where v1 cm prime starts. Now, why do I draw a semicircle? Because we don't know the direction, but we know the magnitude of the vector. And we know that regardless of the direction that it points in, the point that it points to must lie on this semicircle. So, for example, let's say the direction was instead like that, well, the magnitude is known and is fixed. So it must always lie within this semicircle. So that's why you draw a semicircle. And the angle theta here is what we want. So the to proceed from here is just a geometry question. We want to maximize theta, and we have this constraint here. Theta will be maximized if v1 prime vector is tangent to the semicircle that's here. Uh, yeah, this is just a math thing. So I hope you can see why the maximization happens when it's tangent. So now when it's tangent, you have a right angle here, and you can do some trigo. You get theta equals to sine inverse of this, and because this equals to this, you get this sine inverse of this. And from the above relation, or actually from just substituting in, because v1 cm equals to m2 over m1 plus m2 v1, and vcm equals to m1 over m1 plus m2 v1. By just doing this, you will get that theta equals to sine inverse of m2 over m1. And you can see that just by doing this, you saved yourself a ton of work from writing the three equations and then differentiating, moving stuff around, and doing a whole ton of tedious algebra. So this method is very, very powerful and very, very elegant. And it it is quite important lah to know this because tremendously help without it will tremendously help you without making you go insane over algebra. Okay, but before we get too excited to end this problem, we should realize that we have something, we have theta equals to sine inverse of something. We know that this something must be less than 1. So for this to make sense, you must have m2 over m1 less than 1, which means that m2 less than m1. But we didn't specify anything about m2 and m1. So it is actually possible that m2 is smaller than m1. So what happens in this case? Well, our physical intuition tells us that if you have something that's moving and it bounces against something, well, of course, the first thing must record at least. So in this case, if your sine inverse is not defined, then your object will just simply recoil back. So you will, oh wait, my bad. Okay. So your object will just simply recoil back. And if it recoils back, your theta is just equals to pi. This means that you should write your final answer like that when you consider where you consider both cases of M1 and M2. So again, check for extreme cases before you finish the problem. Don't throw away marks like that. Yeah. Okay. So this is what I said previously. You can do this problem without the CM prime at all, but it is not recommended. All right. We'll move on to one more section. Actually, okay. I think we can just go on a short break now. So let's have a 5-minute break before we move on to complete the rest of the content and any questions that you guys have. So in the meantime, if you guys have any queries, you can just raise it up. I haven't been checking your Discord, so I apologize for that. Uh, yeah. So we go on a short break. We will come back at 9:12. Yep. All right. Okay, yeah. Before we come back, if anyone has any like questions about, especially about CM frame, because it might be a bit like foreign to you guys, you can just ask ahead lah. Okay, if not, it's 9:12, so let's come back to this. Okay, so we'll just our last section before the ideas will be work, energy, and power. So uh, should be quite standard concepts, but now we are involving some integrals and derivatives. So uh, so we have KE and PE. You guys should know this, and they are different lah. K is just half mv squared, and then PE you have a lot of different forms of PE that are given here. You should also know that power is the rate of doing work. So uh, this form should be most familiar to you guys, but there are other forms as well. So when we define power, we can either define it instantaneously or we can average it. So instantaneous is at one point, average is over some time. So instantaneous power will just be defined as dw dt because that's the instantaneous rate of doing work. Now, we also know that, uh, oops, okay, we also know that W is F dot displacement, force dot displacement. So actually, dw dt is just F dot dx dt, which is just F dot v, and that explains the second equality there. So yeah, that should be quite standard. So that's just definitions. Now, for conservation of energy, which we usually just call COE, so yeah, we just call this like the COE equation from now on. It states that total energy of an isolated system is constant. So loosely speaking, we can just write uh, sum of initial kinetic and potential energies equals to sum of final kinetic and potential energies. So yeah, nothing too fancy about that. Now we have the work done. So if you have a given force F and you're doing something between 2 points, which we call it Ri and Rf, these are position vectors. Then the work done is defined as that. So here you see an F dot dr, right? So your dr is simply defined as this vector in Cartesian coordinates. And because your F is usually is usually in 3D, so you have Fx, Fy, and Fz. You have three components there. And then you have a dr with three components there. So usually just be you usually just be doing this. And this is just fx dx plus fy dy plus fz dz. Now, importantly, your fx might contain y or z, and so on, and, and so on. Need not just it need not just contain x. So it's not as simple as you might think it is, lah. Okay, so just a mathematical example here. Find the work done by this force between these 2 points through a curve given by this. So this is a bit simpler because it's in 2D. So your dr is just defined like that. You don't have your k term. So your f dot dr is just defined like that. You just put your f in and then you dot your dr, you expand it out and you get this. Now, why do we have to define the curve y equals to x squared? Because if we didn't define this, then there's no way to integrate this. Because at the end of the day, we want to integrate this. But we don't know how y depends on x because we have a dx here and we have a dy here. So by defining this path, we can say dy equals to 2x dx. and then we can sub in the y here, and we make this integral purely in terms of x. And now it's purely in terms of x, we can integrate it, and you get the work done through this path. So yeah, calculating work done for any force and any path is as simple as that. So just always just integrate lah. So the steps is to first find your f dot dr and then you integrate. Yeah, as simple as that. You also have the work energy theorem, which links your work to the change in kinetic energy. So your total work is just the change in kinetic energy. Yeah. Okay. Now we have a special type of forces, which we call conservative forces. These types of forces are special because the work done in moving a particle between 2 points is independent of the path that's taken. This only depends on the initial and final positions actually. And yeah, so because of that, you can ascribe this potential energy function, which we just call U, to be like that. So this is how we define potential energy actually for a given conservative force F. So take note that F is conservative. Yeah. And your work done from point A to point B is just given as this. So it is this. Now, this is not equal to UB minus UA. So it's not final minus initial, it is initial minus final, which may be a bit trippy, but the negative sign is actually really important in this case. So not final minus initial, rather initial minus final. So the negative sign is quite important here. As a consequence as well, if you take any particle through a closed loop, meaning you take the particle, for example, from this point, you go it like that, you move it like that, and then you move it in such a way that it goes back to its original position, then the work done is zero for a conservative force. Reason being, well, your A and B are the same point, so you just get UA minus UA equals to zero. So this should be quite obvious. So some examples of conservative forces are your gravitational force and your spring force. Well, how do you know it's conservative? It's quite easy to tell because GPE and EPE are defined, and you can only define potential energy for conservative forces. In contrast, non-conservative forces include your friction and your air resistance, because you don't have something called a friction potential energy or an air resistance potential energy. It's just not defined. And also, clearly the way you move your object through friction or air resistance will matter in the amount of work done. And when you move it through a closed loop, clearly it still does work. So they are not conservative. So to revise the COE equation in equation 17 here, so to make this equation clearer, we can actually define it in terms of non-conservative forces. Your change in total energy, uh, which is just the change in kinetic energy plus the change in potential energy, is equal to the work done by non-conservative forces. This means that total energy is conserved if there are no net work done by the non-conservative forces. So as an example, if friction is present, you cannot apply COE because non-conservative friction force does work. So all this is just like a mathematical way of saying that, okay, if you have a non-conservative force, you cannot apply COE. Yeah. So this example, we have, and we are finding the electric potential energy given a charge Q and a charge big Q. So this is just a naive application of the definition here in equation 20 for your potential energy. Since you're given the force function, you can simply substitute it in and then integrate. And you should get that your potential electric potential energy is given as such. We will revisit this in electrostatics, so don't worry. So yeah, just take note that when we define potential energy, we usually take the lower bound to be infinity because it's convention that we take our reference point of zero potential energy to just be at infinity. Yeah, by convention. Okay, so that's potential energy. Now, there is some confusion about potential energy when you deal with multiple particles. So let's take a look at this example here. We have two masses, M1 and M2, connected by a spring of constant K and length X. So these masses are traveling at V1 and V2 respectively. Your spring starts with zero length at equilibrium. So the extension of the spring is just equals to X. We are interested in finding the total mechanical energy of the system. So what you may be tempted to do, so you may think, okay, I want to find the total energy. So I want to find the energy of the first mass plus the energy of the second mass. That should give me a total energy. So that's what you may think. So when you do that, you find E1, which is just K1 plus U1 half M1 V1 square plus half KX square. Now similarly for E2, you just get this. Uh yeah, you just get this. Okay, then easy, right? You sum it together and you get this. But this is wrong because you double counted the potential energy by doing this. So what do I mean by double count? Well, the subtle thing is that potential energy belongs to an interaction. It doesn't belong to any specific mass. So it is actually incorrect for you to say that, oh, E1 equals to this and then E2 equals to this, and then you sum them together. Instead, the correct way is to just sum up the kinetic energies because these are truly independent of each other. And then sum up the potential energy of the interaction. So you don't double count in this case. So this is the correct way of expressing the total energy. So this example was kind of simple, but it shows you a small subtlety that you might be confused with. So here, potential energy doesn't belong to any mass, and you should not double count potential energy. So one trick, what one trick to do that is to always look at the number of pairwise interactions between two particles involved. So let's say if you had instead three particles, right? Then instead of finding E1, E2, E3, which is wrong, you want to find you want to consider this interaction, this interaction, this interaction, and then you add up the potential energies of each interaction to find the total mechanical energy. So don't look at the number of particles, look at the number of interactions. Okay, so that's for multiple particle energy. So now just some like partial derivative stuff. So we can relate a conservative force and potential energy as such. This is by definition. So Fx is the force in the x direction and then so on and so forth for Fy and Fz. So these symbols denote partial derivatives. They are called dou. So you can just say dou u over dou x, for example. So this just means you differentiate u with respect to the stated coordinate while keeping all other variables constant. So yeah, this is quite mathematical lah. And actually, with partial derivatives, you can check whether a force is conservative. So using some kind of complicated vector calculus, which you don't need to know how it comes from, you can show that a force is conservative if these three conditions are satisfied in 3D. So yeah, so this is just for you to know, and for you to know how to check conservativeness. You don't need to know why it's true. Again, yeah. And when we talk about equilibrium, we always like to talk about stability as well. So equilibrium exists. So equilibrium, once again, is F equals to 0. We know that in 1D, we have F equals to minus du dx. And if this equals to 0, it also means that du dx equals to 0 at equilibrium. So with this, we can now classify our equilibria into three different types. So first type, we have stable equilibrium. In stable equilibrium, the condition is just like that. So you always want to find, so after you find du dx, you always want to differentiate again to find d square u dx square. And we just check the sign of d square u dx square. For stable equilibrium, d square u dx square is positive at the equilibrium point. For unstable equilibrium, d square u dx square is negative at the equilibrium point. Now we can, so one way to think about this is you can think about this like a, for example, let's say you have a parabola here. You have a ball here. This bottom point is an equilibrium point, clearly, because the ball is at rest there and there's no, and it doesn't like, yeah, it's at rest there and there's kind of like no net force acting on it in a sense, because the normal force and the gravitational force completely cancel out. But if you, for instance, you move the ball up a bit here, then you release it, you let the ball drop. The ball will drop here, they will drop here, they will drop here, they will just keep rolling between these 2 points like that. And eventually, you know that it will damp out and it will go back to its original position. In contrast, if you inverted this parabola and you put a ball here at the top, now even if you displace the ball a little bit, it will just roll off indefinitely. So this is actually stable equilibrium, and this is unstable equilibrium. This is stable because it returns back, and this is unstable because it doesn't return back. So this is just how equilibrium is defined. Stable equilibrium exists if it returns back after a small disturbance or what we call a perturbation. Unstable equilibrium is when it doesn't return back and the body moves further away after a small perturbation. So you also have another type of equilibrium actually called neutral equilibrium. This is much more rare and you basically never encounter it, but just to make it complete, this is the condition for neutral equilibrium. So actually, the import, so actually the more important thing is stable and unstable equilibrium. You'll see stable equilibrium again in the next chapter on oscillations. We'll talk about why stable equilibrium is important for oscillations. Yep. But for now, this is how you check what type of equilibrium it is. There are practice problems behind in the problem set. I think yeah, problem 2.16 where you have to check the type of equilibrium. So that's on stability analysis. Okay, so we'll just quickly move on to the ideas. So we have four ideas here. The first one is on energy and frames of reference. So this is a bit subtle and might not be as relevant, but it might be useful to know. Basically, the idea is that no matter what frame of reference you choose, total energy must always be conserved if it is conserved in one frame. But when you choose your frame of reference, you also have to be smart about it. You wouldn't want to choose any random frame of reference that makes it very difficult for you to carry out calculations. But the thing is, even though total energy is conserved, your kinetic energy and your changes in kinetic energy can differ between frames. So let's just see what I mean here in this example from Kevin Cho. So we have Alice on a car who steps on the gas pedal. We have Bob on a sidewalk, which is basically basically like the rest frame, right? Because it's like the frame of the Earth. And he's seeing Alice's car accelerate from rest to 10 miles per hour. Then we have another guy, Charlie, who is in a moving frame. He's in another car. He sees acceleration from 10 to 20 miles per hour. So you might be tempted to say that there's kind of a paradox here, right? Because Charlie is seeing that the KE of Alice's car is increasing by 3 times as much as what Bob is seeing. So the way to resolve this is actually to realize that the Earth actually has a change in kinetic energy. So yeah, don't forget that the Earth exists. So okay, so working things out in Bob's frame is quite simple because it's just the frame, it's just the rest frame of the Earth. So the kinetic energies, final kinetic energy of the Earth and the car is just given like that, where P is your total impulse given to the car. Uh, so yeah, these are the kinetic energies. So because you're dealing with the Earth here, right? Your mass of the Earth here is huge. So this term is basically negligible. So, but this term is not negligible. This means that the gain in KE of the Earth in Bob's frame is negligible, and the bulk and basically all of the gain in KE goes to the car. But the problem about this is that in Charlie's frame, this doesn't apply. The gain in KE of the Earth is not negligible, and you can just see it using this. Because in Charlie's frame, he's moving with respect to the Earth. So if the Earth is here and Charlie is here, uh, then what Charlie sees is this. He sees that the Earth is actually moving. So the Earth actually has some initial momentum P, big P, because the Earth is not stationary. So you can compute the change in kinetic energy of the Earth as such. And after expansion, you realize that you have this nasty little term here. But the problem is that you cannot do anything about this term because it is only linear in small p. The other term, yes, this tends to zero because it's quadratic in small p, and small p is pretty small. But your other term has a big P term. Big P term is much greater than small p because big P is calculated using the mass of the Earth, which is already massive. So you cannot ignore this term, and this term will exist. This means that the Earth actually decreases in kinetic energy in Charlie's frame, and this decrease in the Earth's kinetic energy will perfectly account for the increase in the car's kinetic energy in Charlie's frame. So energy doesn't go anywhere. It is perfectly conserved, just that some of it is taken from the Earth to move it to the car in Charlie's frame. So that's what this example is saying. So what's the key lesson from this example? When you want to find how energy changes, you almost always want to go into the frame of the larger object. In this case of, and yeah, it's quite useless to go into Charlie's frame in this case because it just overcomplicates things. Okay, the next idea is on extended systems. So this is basically your changing mass system. So just a quick note, it's probably quite difficult for it to come out in a modern SPhO paper because I think the concept here is just a bit more difficult than the difficulty level of SPhO nowadays. But it's still quite important for you to understand what's going on here, so you can better appreciate how force and momentum are related. So let's take a look at this example here. We have a cart of some initial mass moving at a speed v, and you have stand dropping on it at a rate of sigma, dimensions of mass per unit time. And the sand has no horizontal speed relative to the cart. You need to apply a force to maintain the cart at a constant speed, and we want to find this force. So the thing is, for this example, if you just say, oh, okay, F equals to ma, now V is constant, so A equals to 0, so F equals to 0. Well, this is straight out wrong, because clearly you know from daily life that you can't have zero force maintaining this. As your time goes to infinity, you have a lot of sand on the cart. So of course your cart will slow down. Of course you will need some force to maintain the speed. So this is blatantly wrong. What we instead do is we consider the cart and the sand on the cart as having a total mass of m. Now here's where we go back to our good old friend F equals to dp dt. So if this your P of the system is just equals to mv, but your m is also a function of time. If your initial mass of the cart is m naught without any sand, then after time t, this will be your mass of the cart, and you can simply substitute this in. You can substitute this back here, and you can find F equals to sigma v actually. So this is one way to do it. Another way to do it is use the impulse momentum theorem. So this is the impulse momentum theorem, as you've seen earlier. So what we are doing in this case is actually to define a subsystem as the mass in the cart and an infinitesimal mass dm that lands in the cart. Well, in this case, in our subsystem, the change in momentum of the subsystem is just vdm, because the infinitesimal mass dm that lands in the cart suddenly starts moving with a speed v. So let's say this is dm, and then you have m here. Then after a while, your dm goes from 0 to v. So that's the change in momentum. Now after this, it just goes back to uh using the same stuff, and you will also get the same result by applying dp dt. So these are two ways which you can get the result. They are quite similar, but the way of thinking is quite different. So it might be worthy for you to consider how both ways work and choose the one that you prefer. Now, a third way you might have thought about is just consider the expansion, right? P equals to mv, F equals to dp dt, then you just sub this in and use your product rule and you get this. And from this equation, because dv dt is 0, so your F is just vdm dt, which is sigma v. Okay, so you get the right answer in this case. But the problem with this method is that it's not exactly correct, because your system at time t and time t plus dt is not exactly the same. At t plus dt, your system contains sigma dt more sand than the system before that. And your system cannot just change during your analysis. So that is the problem with this method. So it gives the right answer coincidentally, actually. If you apply this method for other sorts of changing mass questions, you will not necessarily get the correct result. So it's just a word of caution to not always consider this expansion naively. So this is not this is not recommended for you to consider. Yeah. Okay. So not recommended to do this. Okay, so this is just a bit more reading for you to understand what's happening. We can look at another example where we use infinitesimal analysis. Here we have a helicopter of mass m and rotor blades of length L, and you want it to have a net downward acceleration of a, which is less than g. Of course, you will need to propel air of density rho downwards, and you want to find this constant speed. So what we're doing here is we consider this mass of air as a cylinder, and we are defining this air with the geometry of the cylinder as such. You can see the picture here. And you see that this cylinder of air will be sent downwards at speed v by the blade at a time dt later if it is currently existing at an instant in time t. So the first step is to apply the impulse momentum theorem. Well, your change in momentum here is just f dt. Nothing fancy about this. So now we start to ask ourselves, what is F? Well, F is the net force, and the net force on this system of the helicopter plus a small cylinder of air is just given by this. It's just the total gravitational force. Okay, so that's your F. Now, what is your initial momentum? Well, initially your air is stationary and is only sent downwards at a time dt later. So your air contributes no momentum at the start. So air contributes no p, and this is purely by the helicopter because the speed of the helicopter is defined to be w. So that's the initial momentum. Now your final momentum, what happens? Okay, your helicopter now has a new speed. Let's call the new speed w plus dw. So this is your helicopter. But now your air has a speed now because it's being pushed and it's sent to a speed of v. So this is your air. And that's your final momentum. So now you just have to plug these results from these three equations back in here. And after a whole ton of simplification and you neglect terms like this because it's second order in infinitesimals, you can do a whole bunch of uh, rearrangement and then differentiation with respect to time. You will eventually get that v equals to this for the helicopter to have acceleration of a. So yeah, after forming these three equations here, it's just a whole bunch of math. So I won't really go through that in detail. The main point is for you to know how to form these equations so that you know how to apply infinitesimal analysis. Yeah. Okay. Okay, let me undo this. Okay. So small remark here. Here we are pushing air from a speed of 0 to v in time dt, which may at first glance imply an acceleration of, well, v over dt, which is infinity. And this doesn't really make sense at first glance. But if you think about it, actually, this mass is also infinitesimal. So the net effect is actually a finite force, which makes sense. So there's nothing contradictory about this question. Nothing is wrong about this question, actually. Yeah. So this doesn't matter. Okay. Last type of problem that we need to know is the pulley problem. So here the concepts are that pulleys are assumed to be massless, which means that if you have something like that, if this is a pulley and you have tension, oops, uh, and you have strings like that providing tensions. If the tension in here is T, then the tension in here must be 2T because you need the net force on the pulley to be you need the net force on the pulley to be zero so that it doesn't experience an infinite acceleration because m equals to zero. So if F is non-zero, then A will be infinite, which doesn't make sense. But we have to be careful about this because even a massless pulley can have acceleration. It doesn't mean that a massless pulley has no acceleration because they can still experience a finite acceleration but have no net force. It still all makes sense because m equals to 0. So yeah, just be careful about that. But the massless condition just means that you can balance forces on a pulley. That's it. Yeah. Another condition is that strings are usually assumed to be light and inextensible. What this means is that firstly, tension is the same throughout the string. Here is what we did. We said that tension is the same here. So tension is the same through a string. Secondly, what this also means is that length of string is constant. And we term this the conservation of string. We'll see how to apply this later. Okay, actually all these three ideas are important. So uh, these three ideas are important for pulley problems. We'll see how to apply them later. So what exactly is this conservation of string that we're talking about? So let's look at example 1.13 to find out. So here we see two blocks and three pulleys, and we have this long string that's winding around all the pulleys. Okay, so like what I said earlier, the total length of the string is conserved. That's conservation of string. So what we're going to do is we are going to define some lengths here. So we have defined x, negative y, and negative z. Now, you might be asking, why are some lengths negative? Okay, so this is just by convention. When we define a length, as we see in point 3 here, you have to imagine how the system moves. So we usually just define positive as lengthening and negative as shortening. So it takes a bit of imagination, but you should try to imagine how the system moves. Now, the thing is that mess up, if you reverse your sign conventions, so you will get exactly the same result anyway. So it doesn't really matter so even if you think m goes down or m goes up before working anything out, it doesn't matter. As long as you're consistent with how you define your signs, even if all your signs are flipped, at the end, you still get the correct answer. So through some imagination, you can see that if m goes down, then this x will increase. Then your y and z will actually decrease through some imagination. It's hard to explain this. Yeah. But we can see that by defining these lengths here, you can sum up these lengths and just be a bit careful with the z because there are actually three strings there. And once you do that, you will get this constraint on the length of your string. And the length of the string is constant. Once you have that, you take the derivative with respect to time twice, and you get this. And you know that the acceleration of mass m is just x dot dot, and the acceleration of mass 2m is just negative y dot dot or negative z dot dot, both of which are the same. So you can just solve this and then find that this is true. So that's how to use conservation of string. There is another example in the problem set which you can try on a pulley. You have to use conservation of string for that. Okay, so one last thing on infinite systems is on perspective. So we'll be dealing with the infinite pulley here, where we have this setup as such. This extends to infinity and just repeats itself. So theoretically, you could just like balance forces and then do your typical stuff and then try to like sum a geometric series or something like that to go to infinity. But a much easier way is to just go into a correct perspective. What this means is that because this infinite system here is self-similar, so if I just took this block, this is just itself. right? Because it's infinite. So we can see in this diagram here that we took this block and it's equivalent to just doing this and replacing this whole block. This whole block is replaced by a mass called M effective. And if we again do this for this small pulley here, we can see that this is again equivalent to having this M effective here, as you can see on the diagram on the right there. So with this idea of M effective, all we have to do is find out what is this M effective. So the idea here is that the tension in the top rope must be the same throughout all the systems because we said that these systems are equivalent. Now it's easiest to find the tension in the top rope in the last one, right? Because this is literally just M effective G equals to T top. Okay, nothing fancy about that. Now for the middle picture, how can you find the tension? Well, this is just a normal pulley system, so you can just solve it simply. And by solving it simply, you can find that the T T in the string that's not the top string, T will be 2m, okay, 2m M effective M plus M effective G. And then by balancing forces on your massless pulley, your T top equals to 2T, and you will get this. So this is your T top. Okay, so now cool, you have two expressions for T top. All you have to do is to equate them with each other, and you can find M effective. I think it's 3m. Yeah, yeah, 3m. So you can just do that. So this is how you deal with infinite systems. You replace it with its so you introduce itself into itself, and then you just replace it with itself, and then you just solve some type of equation that involves self similarity like that. So with this, you can easily find the acceleration of the leftmost mass m, as it's just a simple pulley. So you will see a concept like this again when we cover infinite circuits. The idea of replacing something with itself is important for infinite systems. And yeah, a pulley is no exception to that. All right, so with that, we've come to the end of the content. I understand that I took like quite long, so if anyone has any questions at this point, I would be, I'll just check the Discord again. Okay, yeah, anyone has any questions? Okay. Oh, okay. Oh, okay. Okay, there's a request to do 2.17. Uh, okay, I think we can try to see how it goes. But we'll see if there's any other questions first. If not, I'll answer you like privately. Yeah, because I think most people have not really done the problem set, so it's fine. Okay, if not, I will just I will just go through like one problem or like two from here that I find are quite nice. Okay, okay, I'll go through problem 2.5. So problem 2.5 might look like a standard problem here, but there's actually a very nice way to do it if you look at the comment here. So you just have a tennis ball of M2 sitting on a basketball of M1. M1 is much greater than M2, and you're dropping the balls from a height h from the ground. So when the balls are just about to hit the ground, of course you know that from conservation of energy you have 2gh here. And what happens is that your M1 will rebound up with 2gh, and your M2 will go down with 2gh. That's why I said here. So yeah, now you want to find the maximum height that the tennis ball goes after the collision. So okay, you might you can work this out normally in the lab frame, right? So you can just okay, you have these now, you have these criteria now. You can just conserve momentum and then either use epsilon equals to 1 or conserve energy. Both ways work, and you can find the final speed of M2 after the collision, and then in turn find the final height. That's perfectly fine. But a much easier way to do this is actually to just use the CM frame. So what does this mean? Okay, the first important thing is that M1 is much greater than M2. So when you look at the CM frame, right, recall that your VCM okay, is this. But since one mass is so much greater than another, then you basically can just ignore M2. At this point, this is just roughly equals to V1. So what this means is that actually the CM frame is equivalent to frame of M1 because of the M1 much greater than M2 condition. So why is this useful? Because if you go into the CM frame, which is the same as going into M1's frame, you have this. Because you're in M1's frame, M1 will be stationary. And recall that to go into the new frame, your M2 will be 2 square root 2gh downwards. This is the situation in the CM frame. Now, you can think of M1 as stationary. So M1 is basically like an immovable wall in this sense. And also because M1 is so large, right? So it's basically like an immovable wall. So when M2 collides with M1 in the CM frame, what will happen is that M1 will stay put. Then M2 will just rebound back with the same velocity that it came from, because this is just like throwing a ball at a wall and having an elastic collision. So M2 actually just goes back like that in the CM frame. Uh, then with this, so after this, remember to go back to the lab frame. And when you go back to the lab frame, this is just going back to M1's frame also. So when you go back to M1's frame, you add a speed of 2gh upwards. And this will become 3 square root 2gh. And this will imply that the maximum height will be 3 square root 2gh square over 2g, which is 9h. Yep. So by taking a look at this, you can see that going to the CM frame is actually very, very elegant. You completely don't have to do any calculations at all with your COM, COE equations, or even your COR. You just got this instantly by just going to the CM frame and then going out. So when you have a case where you have a collision and one of the masses is much larger than the other, it might be worth considering how you can use the CM frame in order to simplify how your things work. And in this case, it did, and you got the answer quite easily without any hard calculations. So yeah, that's problem 2.5. As an exercise, you can try not using the CM frame at all and see how it goes with COM and COE. Yep. Okay. Uh, okay, it's already later than 10, but I think I will just go through one more problem and then we'll call it a day. I will go through problem 2.9 on the rocket. So here we have a rocket of initial total mass m, then it gives out fuel, right? And the fuel is ejected opposite to the rocket's direction of motion at a uniform mass rate b, which is mass per unit time, at a speed u relative to the rocket. So this is important, relative to the rocket. So now we want to find the speed of the rocket as a function of time if the rocket travels in zero gravity. So this is where we use our infinitesimal analysis. So let's say that at some point in time, your rocket is like that. Let's say that your rocket has mass small m, which is lesser than big M. Then it gives out a fuel of, let's say we call it d mu. Okay, so it gives out a fuel which we call d mu, and it's opposite to the direction of the rocket. This means that in a short time interval dt, the rocket's mass decreases by d mu. So your new mass is m minus d mu. And if your rocket is moving at v at this point in time, then your ejection speed, because it's ejected with speed u relative to the rocket, your ejection speed will be u minus v plus dv, where v plus dv is the new speed. So now, how do we write our impulse momentum relation? So dp is pf minus pi. Pf, or okay, maybe it's easier to write pi first. Pi is just minus pi is minus mv because that's just the rocket itself. Then pf consists of the rocket and the fuel. So for the rocket, that will be m minus d mu v plus dv. And for the fuel, because it's opposite in direction to the rocket's motion, it will be negative of d mu u minus v minus dv. So this is rocket, and this is fuel. Now, we just have to expand this, and as usual, you can ignore all terms that are second order or above in infinitesimals. And then you eventually get this. Yeah. So now, what do we do at this stage? Well, mass is obviously conserved, right? Because your mass of the any mass of the fuel has to come from the rocket. So actually, we can write d mu equals to minus dm because any mass that the rocket lost must go to the fuel. So with this will become mdv plus u uh plus u plus udm. Now, in question I, we said that the rocket travels in no gravity. If there's no gravity, force equals to zero. dp dt equals to zero. So dp equals to zero. So we just have mdv equals to minus udm, and we can just do dm over m equals to equals to minus 1 over u dv. we can integrate both sides, and you should eventually get uh after some rearrangement, you should get this u ln uh u ln big M over a small m, big M over small m, which is just u ln big M over m minus bt, because m equals to big M minus bt. So that's for zero gravity. And for and when there is gravity, when there's a downward gravitational field, your F is no longer equals to zero. Instead, your F equals to minus mg. Now, why the minus sign? Because this gravitational force will decrease the momentum. So yeah, the negative sign is important. So we now have dp dt equals to m dv dt plus u dm dt equals to minus mg. Now we can this means that m dv plus u dm u u d u dm equals to minus mg dt, and we have dv plus u dm over m equals to minus g dt. Now we integrate, integrate, and integrate, and eventually you should get this after a whole bunch of rearrangement. And these are your two answers for I and II. Alright, with that, I think, okay, this problem set is relatively long, and also there have been two new problems that have been recently added actually. 2.18 and 2.19 for those of you who downloaded it a while ago. So you might want to check it out again. But anyway, feel free to work these out, and you can send in your solutions anytime, and yeah, I'll be more than happy to help you have a look at it and mark it for you. Okay, if not, I think that's enough physics for today. So we can call it an end for today's lesson. So thank you guys for coming, and you guys are free to leave if you have no more questions. Yep, thank you.